Let's think about now how we're going to calculate these probabilities, right? We have the general idea, right? It's the long-term relative frequency of an event. How likely is it going to happen or occur? Well, how do we calculate that? Well, sometimes we can actually calculate it because we have very finite values there. We have numbers that allow us to do that, right? So for example, on a roll of dice, right, a standard six-sided die, what's the probability it's even? Probably that's even is just there's three even numbers out of six. So we write that as a fraction or a ratio, 3 out of 6, which turns into a decimal, turns into 50%. Right, so that's a very straightforward way of thinking about, and we can calculate it versus me saying, what's the probability that if someone gets married, they get divorced? Well, there are a lot of things and variables that go into that, right? And so that's not an exact calculation. It's more of an estimator, what we call subjective probability. We use all the data we can to make an estimate, but we don't have an exact answer, like with rolling dice. Now, there's a language we have to use when talking about probabilities, this capital P of A, like that, what you see here. To calculate that, you'll see it in the fractions, the number of outcomes of event A divided by the total number of outcomes, right, in our sample space. So that's where you get that 3 out of 6 on top. And this example here, what's the probability of rolling a 3, considering that dice again? That's 1 out of 6. And notice the shortcut notation. Instead of me saying, what's the probability of rolling a 3, writing that out, we can say P, roll a 3, and then generally know what we're talking about. And 1 out of 6 turns into a decimal, and we know it's about 16.6. So keep in mind, which one do we use? They're all correct, all these representations. It's just which one makes more sense to you, which one makes more sense to the person you're trying to communicate this to. Now, if we were in class, we would have a short class discussion around some of the language, because sometimes probability statements in the world can be misleading. The probability that you will die from a bee sting, sorry, I can't say it, a bee sting is 15 times higher than the probability that you will die from a shark. Right? We know sharks are maybe more deadly, they're scarier, but a bee sting kills. So what's misleading? Well, it's probably because bees are more prevalent, right? We see bees. We're more likely to be around bees. People have allergies to bees, right? You need to be in the water to be attacked by sharks. If you never are in the water, you're not going to be attacked by sharks. So statements like this you got to be careful of because of these underlying variables or these lurking variables, right? Talking about an older module. And then two correct ways to interpret this. Well, a correct way in the long run, about 15 times more people die from bee stings than from shark attacks. That would be this understanding, right? With no evaluation around scarier or deadly. In general, again, it looks like bees are more deadly because we're more um, around them more. They're prevalent more. So something to think about there. And to finish this section, we introduce a couple of ideas in probability, something called the complement. There's a little notation. You'll see a little a with the, we call that prime, a prime, or a to the c, like it looks a to the power c. It's the complement. We're interested in the complement sometimes when talking about probability. The complement is the not part. So you can see in this example here, if it's a 40% chance of rain, then the probability of not raining, or the complement of raining, is 60%. That's when you have these binary options, two options, or we're thinking about. It's always 1 minus that, and that's what that formula says here, 1 minus that. So we solve probability problems many times using the complement because it's easier to calculate the probability just by doing 1 minus, right, than actually trying to do a calculation. And then lastly, for this section, an important idea that comes up in the rest of this module and in the class, this idea of what we call conditional probability. What's the probability of something happening given we know something already occurred? And many people think in our world, many of our life is conditional probabilities because the probability of something happening is always dependent upon something having occurred first in some general way, and we use that bar notation. We'll talk more about this in upcoming sections, but this very short example, the probability of getting an odd number is 3 out of 6. There's 3 odd numbers out of 6. What if I tell you, what's the probability of getting an odd number if I know the roll is greater than 3? And then that turns out to be 1 out of 3 because there's one number that's odd that's greater than 3, greater than 3. So that's 1 out of 3 because there's only 3 numbers greater than 3 and there's only one odd number. So you notice how it changes, right? That changes the analysis in some way. Later on, we'll use this formula here. Here's the formula. What's the probability of A given B already occurred is the probability of A and B divided by the probability of B. Now, we don't have our ability yet to do this. We'll practice this. Another way we think about this when we have tables of values, when we organize our data that we collect, is with the number of outcomes, right? The probability of A given B already occurred is equal to the number of outcomes of A and B happening divided by the number total of outcomes of B, and that's what that N stands for.